Okay, so this is the last little section of this PowerPoint. It's just got a few problems to work, and then we should be done. So we've already done the formula about radioactive decay, the exponential formula, and this last little relationship talks about how could you figure out the activity if you happen to know how many nuclei are present at any given time. And so you can do that by using this formula that says the activity at any given time is equal to the decay constant, which remember is 0.693 over the half-life, times the amount of radioactive nuclei present at that time. So this, if you remember, the radioactive nuclei, they fall off as an exponential, e to the minus lambda t, and the activity also falls off as an exponential, e to the minus lambda t. So at any given time, you can figure out the activity just by multiplying the amount of nuclei present times the decay constant. The result of this, the resulting concept, is that if you have a shorter half-life, you're going to have a larger decay constant, and your sample is going to be more active. So shorter half-lives that are half second, a second, less than a second, those really fast half-lives are really, really active samples because they don't have much time to decay. They have to decay very quickly because their half-life is fast, is very short. So they tend to be more active samples. So when we talk about dangerous nuclear radioactivity, it's the short half-lives excuse me, that are the problem, because those are the ones that are the most active samples, and they're decaying at the fastest rate, and they have the most radioactivity in them. The long samples, like uranium-235, which has a half-life of like 10 to the 9th years, is really not that active of a sample and wouldn't be as dangerous, believe it or not. Issue is that, of course, it's active for a super long time, but it's not very active because the activity of that one is not going to be a lot. You're not going to get a lot of decays happening every second. Okay, so we'll do a couple of examples. What's the activity of a sample of carbon-14 that contains 3.1 times 10 to the 20 nuclei? So for this one, the number of nuclei present at the time that we're asking about is 3.1 times 10 to the 20th nuclei. And the weight, the lambda for carbon-14 is 0.693 divided by its half-life. And its half-life is 5,730 years. So that gives you a decay constant of 1.21 times 10 to the minus 4th inverse years. Okay, so our activity is going to be the lambda times the number of nuclei. So you can multiply those two together. Now the issue, you would say 1.21 times 10 to the minus 4th inverse years times 3.1 times 10 to the 20th. That's going to get you a number that's going to be in decays per year. That would be the unit, because this is inverse years, and this one happens to be nuclei, so nuclei per year. If you want to convert that to nuclei per second, which is what we usually like to do, then we would end up converting that from nuclei per year to nuclei per second. The final answer on that is going to be 1.19 times 10 to the 9th decays per second. So if you can check your numbers, get it in decays per year, and then convert that into decays per second, that'll tell you how active that sample is, of that particular sample of carbon-14. Okay, another example will work, and then I'll let you work the last one yourself. How many nuclei of uranium-238 remain in a rock if the activity registers 640 decays per second? So in this case, the activity is 640 decays per second. And they want to know how many nuclei are remaining. So again, you're going to use your decay constant for uranium. And you're going to find that it's going to be 0.693 divided by the half-life. But the half-life is in years. It's 4.468 times 10 to the 9th years. So if you need this to be in inverse seconds, because your activity is in decays per second. So we're going to go ahead and convert it just right here in the denominator. A year is 3.1536 times 10 to the 7th seconds. So that's how many seconds are in a year. You could work it out. You could do, years, 365 days, 24 hours, 3,600 seconds. That's just what you're going to end up getting. So when you work that out, you get your decay constant of 4.92 times 10 to the minus 18 inverse seconds. That's the decay constant. So now you can find your n value by taking your activity and dividing by your decay constant. That's the formula. And so when you work that out, you have 640 divided by this decay constant right here. You end up with 1.3 times 10 to the 20th nuclei for that particular sample. So that's how many nuclei are in that sample at that time, if the decay activity was 640 decays per second. The last problem is a little trickier. You have to figure out the mass, so you're going to have to use the atomic mass of that one. The final answer, I'm going to let you work it out, is 7.73 times 10 to the minus 4th kilograms. So you can see how that is going to work, which if you do it in U's, it's 4.6 6-ish times 10 to the 23rd U's. So depending on how you work that out, I don't think they told you what unit to put the mass in, so you can leave it in U's if you want to. So you're going to work that out. Once you get to the number of nuclei, you have to just convert what mass that equates to, because you can do that because you know the mass of each atom. So you can do the conversion from number of nuclei over to the mass, the total mass of the sample. So that's that third problem, and you can work that out. And then there's one more problem about cesium-124, pardon me. I'm going to give you the answers to this, and then actually, I don't have this one worked out, so we're going to have to work that out. I don't actually want to work it out right here. I want you to do it on your own. So what we'll do is we'll check it in class. So I want you to work this one on your own. We'll check it in class, and we'll figure it out. So it's kind of one that encompasses everything. It's got the exponential decay, because you have to figure out how much is present 2 minutes later. It's got your activity. You have to go from mass to figure out how many nuclei there are. There's this whole thing. So there's a lot of stuff going on in this problem. So we'll work that out, or you work it out. We'll check your answers in class, and that'll be it.